So we build a model. The issue of this model is that model is in fact incorrect, which means that our model is not perfect. So that's the issue, because we do not know the true model. I mean, in the simulation model, you can specify true model, but in the real data analysis, you don't know what the true model is. However, our model is useful because it provides a nice summary and valid inference for data. So let's look at this the classic example, which is the Anscombe's quartet. So it compromises the four data sets that has the same summary statistics, but they are very different when you graph the data. So four data set, their mean and variance, they are the same, and mean of y, variance y, up to 2 decimal, they are the same. Correlation, linear regression line, they are the same. I mean, up to some decimal points. So they have same summary statistics, but they are very different when you make a graph. So this first graph here, it is reasonably assumed this linear regression model, right? But for the second data set, even though they have same summary statistics, it is not reasonable to use the linear regression model because they have the curve. There is a curve. And for third one, it's okay to assume the linear regression model, but there's a some point which is deviate from the rest of the observations. And the fourth one, it is not reasonable to have a linear regression model. And then there is also another extreme point. So this Anscombe's quartet gives us the lesson that we need to be careful when we do linear regression model, and then we have to check the assumptions after we fit the model. So in the SAS for multiple linear regression model, we use the proc-reg and the model statement, which is same as a simple linear regression. So let's look at this example. So this data set called crime appears in the statistical methods for social sciences in the third edition by Alan Agresti and Barbara Finlay. There are several variables: state ID, state name, crime, and murder, and PCT metro, PCT wide, and PCTS, poverty, and single. So here our interest is to look at association between crime and other factors. So how the crime would change by the change from the possible factors. So dataset has the 51 observation and 9 variables, and we fit the model crime on PCT metro, poverty, and single. Then same as the linear regression, simple linear regression, we have the 3 components in the data, the output. So first one is analysis of variance. So this sum of square model, sum of square error, and sum of square total. And then there are mean square from regression, mean square due to error. And we have x value dividing by mean square of the regression divided by mean square of error. And then you can see that this probability of the F statistic is the less than 0.001, which is less than 0.05. So this means that the model is significantly different from the null model. With the null model is the model with only intercept. So it means that our model is the useful. So here we can reject the null hypothesis and conclude that our model is useful. I mean, at least one of the coefficient from the covariates is not 0. When we have R square, which is 0.84, means that the variability of y due to these three variables is the 84%. So means that the variability of the crime is explained by PCT metro and poverty and single. That percentage is the 84%. And then here the next step is the parameter estimates. So this parameter estimates are the estimated regression coefficients, and this is the standard error of the regression coefficients. And then this is a t-value, which is from the t-test. We are doing a t-test on this statistic. And then these p-values are less than 0.05, so which means that these four regression coefficients, they are significant. So we can get the estimated regression model. So interpretation of this model is that provide that all other covariates are fixed, 1 unit increase of poverty will increase the 17.68 units of crime on average. So which means that the poorer, then that there is just more crimes. And then for single, for example, after fixing the other covariates, PCT metro, and fixing PCT metro and poverty, 1 unit increase of the single is leads to increase of the 132.41 units of the crime on average. So more single and it means more crimes. So far everything is okay. Then the question is our model okay? Is it right? And then for that one, we need to do the regression diagnostics before we draw the conclusion from the fitted model. So, I mean, people usually think that if they fit the model, then they think that that's the end. But that's not the end. It is very important to check the regression assumptions and issues of collinearity and the inflation points that I mentioned before. So here I will talk about how to use SAS to check whether your data meet the assumptions of linear regression. So we can check the linearity on here, which means that the relationship between predictors and the outcome variable should be linear. Then you can use the two methods. One is the scatter plot. So as we talked before, we can use the proc SG scatter to plot the scatter plot matrix to check the trend of the data. So when you look at that, the relations between the crime rate and each variable is very close to the linear. Although you can see that there's one data points are far from the another data points, the rest of data points that I will talk about it later. But just looking at trend, they are likely to be linear. The second method is to look at the residual plot. So in the residual plot, after residual is the left over from the fitted model. So there should be no pattern between residuals and fitted value or predicted value, because these two are independent of each other. If there's a pattern, then our model has a problem, because there is a part that is not that there's the part in the model is missing to explain the total to explain the variability of the model. So I mean, the residual should be the leftover, so there should be nothing systematic thing left in the residual. So residual and the fitted value should be graphically there should be no pattern. So if you run the proc-regs, it provides the various diagnostic plots. So this R residual means raw residuals, which is the yi minus yi effect, where yi hat is fitted value. And R student means which is called studentized residuals. Predicted value is the fitted model from regression model. And when you look at that, there is no pattern between residual and predicted value, and also no pattern with the studentized residual and the predicted value. They are scattered along this along with this line 0, the horizontal line. So we check the linearity, then there's no problem. Then second thing we need to do that is we need to check the outliers. So outliers is the observation that numerically distant from the rest of the data. So it is usually the extreme values. So in the regression analysis, the studentized residual exceeds +2 or -2. The points are potential outliers. If their studentized residual exceed +3 or -3, they are outliers which should be concerned very carefully. So you can use a scatter plot, and then you can see that there is a one data point is far from the other data points. And then you can use the proc SG plot to check what this data point is. So I use the SAS code, putting the data level as a state option. So we can check the outlier in this example. So you can see that DC is the outlier. So this DC observation is far from the other data points. And then second method that we can use is residual plots. So let's look at the residual plots greater than 2 or less than -2. Then we can check that there are 3 points. And we can check these 3 data points by using the output statement. So we can use the output statement to get the information of fitted model and the diagnostics information. And the output statement is you can put the output, use the output statement and out, and then I set the name of the data set from of this output is a crime 1 res. We keep ID, state, crime, PCT, metro, property, single, and R. And this R student returns the student type residuals. We name it R. So, and these are the other keywords. So you can draw many diagnostic information from the diagnostics by using this output statement. So let's look at what exact values of these outliers and who are these outliers. And we can sort by this student type residuals. So this crime 1 res, we use the output statement and we draw the diagnostic information from the fitted model and stored in this crime 1 res, and we also store the student type residuals, this R, and we sort by R, and then we use a proc print, and then we first print first of 10 observations. So this by proc sort, we sort by the ascending order. So by sorting, we can, when we print out first 10 observations, we can see the smallest 10 observation. So we print out state ID, state, and R. And then since we have 51 observation total, so the 51 observation in this crime 1 res is contains the maximum value of the R. So we print out the last 10 observations. Then we can see that the Missouri has the the state MS has the smallest student type residuals, and this absolute value is the greater than 3. So we can think that this is the outlier. And Florida and DC, they are greater than 2. So this Florida is possible outlier, and DC is the outlier. So that we can check these DC, MS, Florida are they are 3 outliers. So after confirming that we have outliers, then how can we deal with them? So practice, you may go back to the data and then check why this outlier happened. So maybe the mistake, or maybe it is reasonable. You may delete them for your analysis, but you have to be very careful of that, because the outlier can be the influential point, which means that it may change your regression fit. So I'm going to talk about the influential point in the next lecture. So in the next lecture, I'm going to talk about the leverage points and influential points, and check normality, and check the homogeneity of variance, which means that the error variance should be the constant.